Hey guys, today we're going to talk about what's called a parallel plate situation. So ignoring the middle plate here, here's kind of your parallel plate situation. You got one plate at one voltage, you got one plate at another voltage, and you might be doing a couple of things. In this particular situation, you're interested in the velocity of the particle at the end. And so basically it's at a certain voltage here, it's at a certain voltage when it hits the other plate, and you can do a before equals after using your potential energy equals your electric potential or voltage times charge. So you've got zero potential energy here, you'd have a negative potential energy here plus kinetic energy. So the magnitude of your positive kinetic energy is equal to the magnitude of your negative potential here. So before equals after for a lot of parallel plates. But another interesting thing about it is the electric field strength is actually identical everywhere between two plates. So if it's 5,000 newtons per coulomb to the right at this point right here, it's at 5,000 newtons per coulomb to the right at this point here, and 5,000 newtons per coulomb at this point here, and 5,000 newtons per coulomb to the right at this point here, and blah, blah, blah. So it's identical everywhere. It's a bit of an approximation, but it works really well. You get sort of changing things right around the edges, or if the plates are too far apart. But in general, we'll be using this formula for that. So let's go through the three things I've written. Electric field strength is constant everywhere between the plates and points towards the more negative or less positive plate. Because remember, electric field strength always points in the direction of positive charge will be pushed, and it'll be pushed either towards the more negative or less positive thing. If you've got a question like the one we were just talking about, you're using energy before equals energy after, and your potential energy is your voltage times your charge. You can also just use change in voltage, because that's really what you're interested in. If you found the change in potential energy, you can set things up pretty much. I tend to think of it as like a before equals after, like roller coaster style question, only instead of MGH right now, we've got VQ. And if you remember when we did conservation of energy, we were able to set our height to be zero wherever we wanted. Just to make the equation easier, so we didn't have a potential energy term on both sides. We could say, hey, this is at zero potential energy. So a lot of times I will decide that this is at 0 volts, pretend it's at 0 volts, and this would be at 500 volts. As long as the difference remains the same, it still works great. All you got to do is preserve the difference, but you can decide your zero level as whatever you want, and you'll still end up with the same answer. Alternatively, you can just have your potential energy. You can just have a term on either side, or you can have negative potential energy. That works great too. Anyway, so your potential energy equals your electric potential, your joules per coulomb times coulombs. Q is charge, remember. All right, now the really new part is this guy. The electric field strength between two plates is equal to the voltage difference divided by the distance between the plates. So this is how far apart the plates are. The width of the plate doesn't matter at all. It's usually there just to throw you off. Yeah, so if you want the electric field strength, the newtons per coulomb, just take the difference in voltage, the difference in electric potential between the two plates, and divide by the distance between them in meters. Yeah, so here's an example of the sort of question you get. A lot of times, again, you get the width of the plate, but that is useless to you. You want how far apart they are. That will be your D in your formula. So for this particular question, what you do is you'd figure out the electric field strength between the two. You've got a 230 volt difference between the two plates. Divide that by 0.12 meters. You've got the electric field strength. It will be directed up because it's going from big potential energy towards small potential energy, just like rolling down a hill, like big height to small height. The helium nucleus, the positive thing, will be head towards the less positive or more negative side. So we deflect it up. If we want to know the magnitude of the acceleration of the helium nucleus due to these plates, what we do is once we have the electric field strength with this formula, we multiply it by the charge of the helium nucleus, which is 2 times the elementary charge, 2 times 1.6 times 10 to the negative 19. So here's us finding the electric field strength using our voltage difference divided by the plate separation. We get our electric field strength pointing up. And then if we want to find our force, it's equal to the electric field strength times the charge. So our electric field strength we calculated before, and our charge is the same charge as 2 protons, because that's the positive things in the nucleus, the alpha particle. So 2 times the elementary charge. We get our total force on the thing, and then we just divide by its mass, which is basically the same as 4 protons, because a neutron weighs about the same as a proton. That is how you do something like that, and I hear the ideal length of video is 6 minutes, so hopefully this wasn't that bad. Thanks for listening.